In this video, we look at the magnetic properties of an electron and how these affect its energy in a magnetic field. We have seen that the electron has two angular momenta, orbital and spin. Visually, the orbital angular momentum is due to the electron orbiting around the nucleus. And the spin angular momentum is due to the electron spinning around its own axis. Now, the electron is a charged particle, so the fact that it spins around its axis constitutes a circular current. This electrical current generates a magnetic field. The field lines go like that. Here's the electron. And these are the field lines. The spin points in this direction. The spin is therefore associated with a magnetic dipole moment. The spin magnetic dipole moment, μs, is proportional to the spin angular momentum. μs equals to negative g times e over 2 me times s, where s is the spin angular momentum, μs is the spin magnetic moment, and g is a g factor that equals to 2.00232 for an electron that is on its own, outside of an atom. The negative sign stems from the negative charge of the electron. Therefore, the spin magnetic dipole moment and the spin angular momentum have opposite direction. So, the electron is magnetic. You can roughly picture it as a tiny spinning spherical Bohr magnet. Now, in an atom, the electron orbits around the nucleus. This also constitutes an electric loop current. And therefore, it is also associated with a magnetic field. The field lines go like this. The orbital angular momentum gives rise to an orbital magnetic dipole moment, which is given by μl vector equals to negative e over 2 me times L, where L is the orbital angular momentum. Again, the negative sign here is due to the negative charge of the electron, so μl and L have opposite direction. There are several consequences of these magnetic properties of the electron. One of them is that the energy levels of the atom are shifted in a magnetic field. This is called the Zeeman Effect. Suppose we have a magnetic field along the z-axis. Any magnetic moment in this magnetic field has an energy that depends on its orientation relative to the field. Just think about a compass needle, which is a magnetic moment in the magnetic field of the Earth. If the two are parallel, the energy is lowest. If they are antiparallel, the energy is highest. Formally, the energy is given by a dot product. E equals negative mu dot B, where mu is the magnetic moment, dipole moment, could be either spin or orbital, and B is the magnetic field, with SI units of Tesla. Therefore, you can see that the magnetic moment has SI units of joule per Tesla, since the energy has units of joule. The quantum version of this reads Hamiltonian H for the Zeeman effect equals the negative mu vector operator dot B. We'll have to add this Hamiltonian to our standard Hamiltonian with the kinetic and electrostatic terms. Now let's look at the bare electron without the nucleus. It has two stationary states, spin up and spin down. Without an external magnetic field, these two states have the same energy, but when placed in a magnetic field, these two states differ in energy. With spin up, the magnetic moment points down since they're antiparallel, and consequently, the energy is high. We correspond to this state. With spin down, the magnetic moment points up, parallel to the field, and the energy is low. The energies of these two states are obtained by combining this with this equation here. And we get E equals positive G times EH bar over 2 ME times B times M sub S, where B is the strength of the magnetic field and ms is either plus 1/2 or negative 1/2. The factor EH bar over 2 ME is commonly abbreviated mu B, and it's called the Bohr Magneton. The orbital magnetic moment also leads to a Zeeman effect. The energy of an orbiting electron in a magnetic field depends on ml. If we disregard the spin for a moment, the energy due to orbital moment alone is E equals to plus mu B times M sub L. For example, in an L equals 1 state, the projection number M sub L can have values of -1, 0, and +1. The -1 state has overall negative energy, so it's lowest. The 0 state has 0 energy, and the +1 state has a positive energy. In a hydrogen or light atom, all these splittings and shifts are usually very small compared to the kinetic and electrostatic energy term in its Hamiltonian. Of course, we will have to consider the spin and the orbital angular momentum at the same time. So these equations here do not give the full picture. In summary, the following things are important. First, the electron has an intrinsic magnetic moment due to its spin angular momentum. Second, in an atom, the electron acquires an additional magnetic moment due to its orbital angular momentum. And third, the Zeeman effect. In a magnetic field, the two magnetic moments lead to energy shifts. Different spin or orbital states have slightly different energy.